The JWST, or James Webb Space Telescope, has disclosed a remarkable phenomenon: illumination shafts coming from a region that resembles a metropolis, lighting up a section several light decades away. This discovery has reignited enthusiasm about the potential existence of intelligent life on other planets. The telescope focused its attention on Proxima Centauri b, the nearest planet beyond our solar system, and noticed something different: luminous pulses. Might these transmissions signify the presence of a sophisticated alien civilization? Stay alert for forthcoming revelations. For scholars and the general public of all ages, the possibility that there is life beyond Earth has been captivating. Any indication that suggests life elsewhere in the universe has sparked widespread excitement. However, a crucial advancement took place when the James Webb Space Telescope provided enticing proof suggesting life among the stars. While surveying the immense reaches of the entire universe, this potent instrument discovered an extraordinary thing on a distant exoplanet. It cataloged light similar to those made by alien urban structures, which stokes the rumor that it could be the home of a galactic city on a far-off world. This hypothesis has sparked a great deal of curiosity and awe within the scientific community, as it may signify the long-awaited breakthrough, suggesting intelligent entities managing societies in ways we're only beginning to realize. Observing these urban-like illuminations from an incredible distance of 4 light-years, NASA researchers are astonished and considering how long the lights may have endured, quietly awaiting our detection technologies to advance sufficiently to perceive them. David Kipping, an astronomer at Columbia University, has characterized the planet displaying these lights as particularly complex. Unlike most terrestrial planets that absorb the sun's energy and release it as infrared, this exoplanet behaves differently due to its unusual interaction with the star it orbits, Proxima Centauri. This revelation emphasizes the James Webb Space Telescope's essential role. Its capacity to gather infrared emissions was vital in detecting the odd characteristics of Proxima Centauri b, which is fundamental for interpreting the planet's atmospheric traits. Researchers intend to continue utilizing the telescope to examine the planet's atmosphere in greater detail, seeking to ascertain whether it could sustain life. The JWST is particularly sensitive to infrared radiation, enabling it to monitor Proxima Centauri b's activity even during its evening portion. While many telescopes struggled to identify faint illumination in deep space, the Webb excels at recognizing even the tiniest glint, making it an extremely suitable instrument to determine whether purported city lights on the planet's dark hemisphere are real. This telescope can detect light from outside sources in space, as long as it is contained within a very narrow frequency range, considerably narrower than stellar light shared by Proxima Centauri b. Its dynamic interplay with its star profoundly influences its milieu. As is true for numerous star-orbiting planets, it gets a lot of power from Proxima Centauri and experiences regular cycles of daylight and darkness. Similar to Earth, a planet that experiences extreme heat when it's daylight and cold at night. It has a long temperature range, largely due to its composition. It possesses a thermal atmosphere. The gap between the illuminated and shadowed hemispheres could be enormous, scorching on one side and icy on the other. This nocturnal thermal contrast is particularly interesting to astronomers, for it provides important information about Proxima Centauri b's configuration in the atmosphere. Thanks to its infrared scanning proficiency, the JWST can adeptly determine the heat emissions from the planet, providing insights into its layer of air. Intriguingly, the Webb's orbit aligns with the orbital period around Earth of Proxima Centauri b, allowing researchers to capture a full record of its daylight cycle, which occurs once every 11.2 Earth days. If the planet is home to an atmosphere, the next step is to analyze its chemical makeup to determine if existence could be sustained. Detecting gases such as oxygen, water vapor, and methane would be a symbol of the planet's potential for life. To accomplish this, scientists scrutinize starlight that traverses the atmosphere of the planet, a method that is hard on the technology. Even though the JWST excels in researching exoplanet atmospheres, its primary mission serves broader objectives. It's especially adept at identifying water vapor, carbon dioxide, and methane, though it's less efficient at detecting free oxygen, an essential biological indicator. Nevertheless, the telescope can look for additional important indicators like ozone, which denotes a robust atmosphere. As they analyze the data gathered by the JWST, the journey to locate distant planets takes less time. This endeavor is gradually bringing us nearer to resolving the ultimate query: is there only us in the universe? Importantly, the JWST can only observe a small number of nearby exoplanets. For more in-depth information on the assessments, astronomers will employ ground-based services like the slated Extremely Large Telescope, or ELT, to commence operation in 2027. The ELT is engineered to conduct deeper explorations of far-flung exoplanet atmospheres, delivering richer and more precise information regarding their habitability. Scientists eagerly anticipate this next era of space tools. In the interim, the JWST remains an indispensable resource in the quest for distant worlds. Despite its limitations, it continues to yield critical discoveries that may transform our perspective on the universe as it exists beyond our solar system. Researchers have high goals for forthcoming space observatories. Their aim is to build devices that obstruct starlight interference, allowing for clearer observation of planets in orbit, similar to shading your eyes to perceive dim illumination. These new telescopes will center on the faint reflected light from exoplanets, aiding in the analysis of their atmospheres and evaluation of their ability to sustain life. That is no frivolous goal. Stars shine with such overwhelming brilliance that they frequently obscure the planet's faint glow. This brightness makes the observation of subtle glows essential for examining planetary features. Scientists are coming up with creative approaches to fix this. One promising approach includes the use of coronagraphs. Install devices within telescopes that shield starlight while permitting planetary light to pass. By shaping and managing how light waves interact, coronagraphs reduce the brightness of the star, making it simpler to observe the planet's dim radiance. Another brilliant concept is the starshade, a made-up spacecraft like a petal of a flower that collaborates with a telescope a distance of thousands of kilometers. It effectively blocks starlight, allowing only the light reflected by the planet to be gathered. This method may be especially effective for monitoring planets within the habitable zone where liquid water and potentially life may exist. However, these advanced systems call for a lot of precision. For instance, positioning. A star shade requires extreme accuracy to ensure effective starlight blockage. Accurate star hue in relation to the telescope over such extensive distances must be precise to the nearest millimeter. They also must be compact, energy efficient, and resilient enough for the hostile space environment. Despite the difficulties, the potential rewards are enormous. Successfully imaging and analyzing exoplanet atmospheres could unveil biosignatures, chemical indicators of living processes. Certain levels of water, methane, and oxygen vapor might suggest biological activity, offering some of the strongest evidence of life beyond Earth. Researchers are also exploring ways to directly capture far-off worlds in greater detail. The next generation of telescopes may utilize cutting-edge optics that correct distortion caused by Earth's atmosphere or telescopic movement, resulting in sharper images. When combined with coronagraphs and star shades, these improvements may enable scientists not only to detect exoplanets, but also to map their surfaces and even monitor their weather. These images would represent a monumental leap in exploring and examining exoplanets and their potential to support life as we investigate progress in the universe. The pursuit of extraterrestrial life grows in scope, refinement, and accuracy. NASA and SETI have reacted to these findings. Future endeavors, including the James Webb Space Telescope, are essential to this mission. Every fresh observation and data transmission draws us closer to answering one of humanity's greatest questions. Are we truly alone in the universe? Detecting lights on Proxima Centauri B, the prologue to a new chapter, could usher in an era of profound change in space exploration. A Proxima Centauri star system, the closest to us, has been significantly examined for decades, yet conclusive proof of life, such as artificial illumination or urban-style brightness, has not been found. Now that the James Webb Space Telescope (JWST) has observed signals, the prospect of eventual contact with intelligent extraterrestrial beings has significantly increased. This type of finding rekindles scientific zeal and public wonder, motivating future generations to explore other planets. As the James Webb Space Telescope continues its mission, it will not only search for artificial lighting, but also research the chemical composition of planetary atmospheres and the fundamental elements essential to life. Detecting biosignatures like methane or carbon dioxide in the right amounts is crucial in determining whether these worlds can support life. The Webb telescope is uniquely capable of deciphering these atmospheric signals in ways no previous instrument could, offering unparalleled insight into the possibility of life on distant worlds. One of Proxima Centauri B's most intriguing features is its position in the star's habitable zone, where temperatures might allow liquid water to flow on the surface. This Goldilocks zone, neither too hot nor too cold, is widely considered essential for life as we understand it. As a result, finding a planet in this zone, particularly one exhibiting potential signs of human-like illumination, is of utmost importance for researchers. Beyond locating life-friendly worlds, future missions will probe the intricate interactions between exoplanets and their stars. Some worlds, like Proxima Centauri B, are tidally locked. One hemisphere always faces the star, while the opposite remains impervious to light. This results in stark temperature variances, influencing the planet's climate and habitability. Comparing and analyzing Earth with Proxima B entails examining produced light, analyzing thermal contrasts and how they affect atmospheric circulation, is crucial to evaluating whether planets of this type can foster life. Progress in starlight preventing technologies, such as coronagraphs and star shades, represents a major breakthrough. Without them, the faint reflections from orbiting planets would be obscured by starlight, rendering in-depth exploration nearly unattainable. By shielding instruments from stellar light, these innovations enable scientists to capture the subtle light that reflects off planetary surfaces, revealing vital information about geology, climate, and possibly biology. Another exciting development in astronomy is the possibility of high-definition photographs of exoplanets. When combined with modern light shielding and adaptive optics techniques, astronomers may soon obtain photographs detailed enough to show cloud formations, continents, oceans, and even seasonal weather patterns. These pictures would greatly exceed mere confirmation of a planet's existence. They would enhance our comprehension of its environment and whether it might support ecosystems. As humanity persists in its cosmic exploration and refines its observational capabilities, the importance of the JWST and subsequent missions only intensifies. Its unparalleled infrared sensitivity permits the detection of the faintest emissions, analysis of atmospheric layers, and identification of probable biosignature markers. Because of constant technological breakthroughs and an expanding archive of observations, we now stand at the threshold of potential discoveries that could reevaluate humanity's position in the universe, uncovering artificial illumination or structures resembling cities on Proxima Centauri B, our nearest confirmed exoplanet, may indicate the dawn of a new epoch in space exploration. This project isn't just about gathering evidence. It also raises profound philosophical and existential inquiries. What would it mean to realize we're not alone? How might dialogue with another intelligent species change the world? The attraction to Proxima Centauri mirrors our deeply rooted yearning for meaning beyond our planet. Future space and ground-based telescopes will continue expanding the limits of what we can observe. Equipped with more powerful light filters, sharper images, and more detailed spectral analysis. Alongside biosignatures, the next generation of platforms may even detect technosignatures, evidence of alien technology. With each spacecraft launch and each signal that travels across the void, we advance closer to answering perhaps the most important question of all: are we truly alone in the universe?